Moving into lesson 5, we are looking specifically at asymptotes. And a lot of times in the past, we had rational functions where we talked just about domain. And hopefully, we start to see a connection between the domain of a function and the asymptotes of that function, specifically domain and the vertical asymptotes. And so the essential question that we have today are, what are the asymptotes of a rational function? And the objectives are centered around that question, obviously, and that's finding the vertical, horizontal, and oblique asymptotes of a function. And of course, I want you to be able to sketch a graph, though this would not be a topic that I would want you to be calculatorless, because sometimes that calculator does help with the tiny little differences that we have. I do want to point out that sometimes, and I will slip up and I'll say both of these, I will say oblique asymptote and I will also say slant asymptote. So same exact thing. Also for the context of today, because I don't want to say vertical asymptote, horizontal asymptote, oblique asymptote, and I don't want to write vertical asymptote, I am going to abbreviate that VA, HA, and OA. So when I start labeling those things, those are the shorthand terms that I'm going to use. Okay, so first, rational functions. We've had this conversation before where p of x over q of x are polynomials, and specifically q of x cannot equal 0. Remember, this is a domain restriction. If we divide by 0, that cannot happen, and so we would exclude it using interval notation. What it looks like and what my graph looks like. My vertical asymptotes occur if essentially the graph shoots way up or way down. And the notation that we have there is f of x goes to infinity, that's when it shoots up, and f of x goes to negative infinity, shoots way down. And what that creates is this vertical line that your graph gets very, very close to but never quite touches. That's called the vertical asymptote. So a couple things I do want to mention, and again, this is helpful for graphing. A function can never cross or touch a vertical asymptote. So that you can see that blue line of the graphic, it's very, very close to my purple dotted line, but it never hits it. And most importantly, VAs are exclusions from the domain. Those are your domain restrictions. So we've actually found these before. The only difference is we didn't talk about them in terms of vertical asymptotes. So, and again, the good news is we have the process for it. So as we look toward an example, here's what we do. Set the denominator equal to 0 and solve. That's really it. And so when we start to talk about solving for x, all we are doing is taking a look at the bottom. I am kind of discarding from my brain the top, that -2 for now. And we have x squared minus 5x plus 6 equals 0. Factoring that, x minus 3 times x minus 2 equals 0. And so we have x equals 3 and x equals 2. And so what this means for us is our VAs occur at there are two lines, and that is x equals 3 and x equals -2. Where it gets a little bit dicey or maybe confusing is a better word, we have to do factorization first, and we have to look to cancel as our first step. And so when we seek to look at number 2, I'm going to rewrite number 2 actually into f of x. It's very similar, equals -5 minus x over x plus 5. Similar, but it'll demonstrate what I need first. So the first thing that we're always going to look to do is factor. Obviously, the bottom won't factor, but the top, we can take out a negative sign. And so we can rewrite this as f of x equals, if I take out a negative from the top, we are left with 5 plus x, still over x plus 5 on the bottom. And if we rearrange the numerator, this becomes negative x plus 5 all over x plus 5. And so it's really tempting initially to say something like, well, okay, I'm going to set this equal to 0 and x equals -5. That's my VA. That's my vertical asymptote. That's not the case. And if you look at number 1, it says factor first and then cancel. So what I'm going to do is cancel those out. Notice that the leading coefficients are both 1, even though we don't write that. So this ends up reducing to become -1. What we would do here and how we would write this is there is no VA. There's no vertical asymptote here. But there is a hole at x equals -5. So if stuff cancels and we have no remaining VA, you have to talk about the fact that there might be a hole in your graph. And as that occurs more and more frequently, we'll probably talk through some of those examples in class. Last but not least, oh no, I guess we have a couple more. Okay, so similar setup, x squared over x squared minus 4. We always want to try to factor first. Please do not be the person that goes, oh, these cancel. That's not how it works. You have to have a factor on the top and bottom in order to have them cancel. The bottom will factor then. So this becomes x squared over x plus 2, x minus 2. And then setting the denominator equal to 0, we end up with x equals -2, x equals +2. We didn't have any factors cancel, so there are no holes. And so we are left with a VA, we actually have 2 of them, of x equals plus and minus 2. So we have 2 vertical lines that your graph gets very close to but never quite touches. Because these are equations, I do need that the x equals. If you forget the x equals, you're not telling me that it's an equation, so I do need that piece. Now for real, last but not least, again, we cannot cancel out the x squareds. We don't have a common factor on the top and bottom. Also, if we look at that denominator, that's not going to factor. And so if we look to solve, x squared plus 4 equals 0, subtract 4 over, we end up with x squared equals -4. That's a problem. If I take the radical there, this gives me a complex solution. My VAs, and let's see if I have it on the first page. I don't. With your vertical asymptotes always have to be real numbers. We're not going to have complex asymptotes. So in this case, we would again say no vertical asymptote exists. And if you want to write it this way, that's okay too. In this case, there are no holes to my graph because there's no factors that canceled. It's just we don't have a VA. Moving into horizontal asymptotes. Very similar idea. This is where it starts to shoot far right, far left, and you can see where that graph kind of starts to go to the right and to the left. You have the definitions above, and pretty much what it means as you approach something horizontally, your graph shoots far left and far right. In this example, my horizontal asymptote is actually the x-axis. And you can see that we have 2 vertical asymptotes. Listed there. Notes that are different from before. Your function can cross your horizontal asymptote. It can, but only in situations when you have a middle piece, and that's going to occur. My cross is going to occur at that point. So unlike vertical asymptotes, sometimes your graph does cross your horizontal asymptote. Again, helpful when we go to graph. As far as horizontal asymptotes go, we have 3 different rules. We always factor and cancel first, but then after we do that, we start to compare the degrees. If the degree on the top is bigger, when that happens, there's no HA that exists. And actually, that's when an oblique asymptote exists. If the degree on the bottom is bigger, your HA is always y equals 0. And last but not least, if the degrees are equal, your HA is a ratio of the leading coefficients. Of the numerator and denominator. And so here's kind of the three different setups of the different rules, and we're only talking about HAs here. We'll talk about slant asymptotes or oblique asymptotes later. But if you look at number 1, my degree is 0 on the top because there's no x, and the degree is 2 on the bottom. So this is similar to 2b because the degree on the bottom is bigger. Obviously, 2 is bigger than 0. Notice the top doesn't cancel, or sorry, the top doesn't factor, but technically we should factor this out first. So f of x equals negative 2 over x minus 3, x minus 2. The degree is still bottom on, or still bigger on the bottom, and so we would say our HA is y equals 0. Again, nothing canceled, so I don't have to worry about canceling anything out. This time, I am not going to change this example. I know I changed it last time. I'm not worried about it canceling. If we rearrange what's here, f of x equals negative x plus 5 over x plus 5. If we factor out a negative from the top, because we generally want our leading coefficient to be positive, if I factor out a negative, we'd be left with x minus 5. In this situation, the degree on the top is 1, degree on the bottom is 1, so we are looking at rule 2c. And when I said ratio of leading coefficients, I would look at my leading coefficient on the top, which is negative 1, and my leading coefficient on the bottom, which is positive 1. And so it would be negative 1 over positive 1 or negative 1. So again, HA is y equals negative 1. I want to point out that I'm talking about leading coefficients, not the ratio of degrees. So it's always the number that's in front. And last but not least, we have f of x equals x squared over x minus 9. Nothing to factor here. And the degree on the top is 2. The degree on the bottom is 1. So we are looking at rule 2a, which says that if there is a bigger degree on the bottom, no HA exists. And so we don't have to worry about a horizontal asymptote in that case. Now, in situations like number 3, when we have no horizontal asymptote that exists, we do have a slant oblique asymptote. And so a slant oblique asymptote occurs if we have a polynomial of larger degree in the numerator. If you want to put that more into people words, you're more than welcome to do that. And it might be something like situations where degree is bigger on top. That works for me. And how we find slant asymptotes or oblique asymptotes algebraically, we do the same thing. We factor and cancel if we can, and then we actually divide the two polynomials. So what this looks like, it does not factor at all. And so what we would do is we would kick back into x squared divided by x minus 9 if you wanted to use long division. And we would have to have placeholders. Or we would take the denominator and positive 9 would go there. And our coefficients would be 1. And then our two placeholders would be 0x and 0. And so we would kick back into this process. 1 multiplied times 9, add down, multiplied times 9, 81, add down. And so our remaining would be x plus 9 plus 81 over x minus 9. Now, a few things that I want to point out. We would have gotten the same answer if we used long division or synthetic division, but we can only use synthetic division. When? we have a linear polynomial with, I shouldn't write it like that, with coefficient and leading coefficient, with leading coefficient of 1. So in this case, we had a leading coefficient of 1, so we could use synthetic division. Now, this is going to be kind of weird, and it's above our pay grade in college algebra, but when you talk the concept of limits, in other words, as x gets very, very, very large, as x goes to, I'm going to say 1 million, this fraction goes to 0. So as the numbers for x get bigger, we're actually creating a bigger denominator, which creates a smaller decimal. Now, we haven't had the concept of limits yet, and you won't see it until math analysis, but there's a reason why I'm going to do what I'm doing, and it's because of this fact. As we get a very large value of x, we actually just start to throw out the remainder. And so our slant asymptote here becomes y equals x plus 9 with no remainder. And again, the remainder is thrown out because of the concept of limits. For the sake of what we're doing, just think of it like this. When we have slant asymptotes or oblique asymptotes, we just get rid of the remainder. We toss it aside. But I do want you to know the mathematical reason too, and that is because of the concept of limits, and that's because as we get a very, very large value of x, that number at the very end, that remainder, becomes almost 0. Okay, putting it all together, because I'm going to ask you to do more than just tell me what the asymptotes are. So, reminders. We still have to find the domain, we still have to find the zeros, we still have to find the y-intercept, and we still have to find the asymptotes, because all of these things will help us graph. So x-intercepts, remember, this is set the numerator equal to 0. Domain is set the denominator equal to 0. Y-intercept, put 0 in for all x values. And then last but not least, D is what we did today. And so, let's look at number 1 first. Okay, so the first thing that I want to do is find the domain, and so I'm looking at the denominator. And so, as I look for my denominator here, I'm going to set that equal to 0. That factors into x plus 1, x minus 1 equals 0. And so in this situation, x cannot equal -1 or +1. How we write that in domain form in the interval notation is -infinity to -1, union -1 to +1, union 1 to infinity. So domain's not going away. Just a reminder. Next, we're looking for x-intercept, which says set the numerator equal to 1. So 4x equals 0, divide by 4, divide by 4, x equals 0. So my x-intercept is 0, 0. For C, plug in 0 for every x. So f of 0 equals 4 times 0, all over 0 squared minus 1, which is 0 over -1, which is 0. So my y-intercept is also 0, 0, which I hope you kind of knew that, because if my x-intercept is 0, 0, well, that's my y value of 0 as well. But if you didn't, you just plugged and chugged. And then last but not least, we're talking about asymptotes. So this is the first new thing within this problem. So first, we're going to look at VAs, so vertical asymptote. To see if we have a vertical asymptote, we always want to try to factor. And so our f of x is 4x over x squared minus 1. We've kind of already done part of this. The numerator does not factor, but the denominator does, into x plus 1, x minus 1. And so our VA, we're looking at the bottom. So our VA would be -1 and +1. So x equals plus and minus 1. Horizontal asymptote, we're looking at degrees. The degree on the top is 1, the degree on the bottom is 2. So this is rule, I'm going to say 2e from the previous page, and that is my y-intercept is always y equals 0. There is no SA, slant asymptote, or oblique asymptote, because the degree on the bottom is bigger. If the degree was bigger in the numerator, then we'd have a slant asymptote. So those are the 4 pieces that I'm looking for you to be able to do, and then you kind of take that information and we're going to sketch a graph. Not here, but we will both in class and right before you do homework. Okay. Next one. Same colors, so green first. Okay. What we're looking for is my domain. So we focus on the bottom. X plus 1 cannot equal 0. So this becomes x can equal negative 1. How we write that in integral notation is like that. Next, looking for x-intercepts. We set the top, the numerator equal to 0. X equals negative 4. So our x-intercept is negative 4 comma 0. Y-intercept, plug 0 in for every x, so that becomes 2 times 0 plus 8, all over 0 plus 1, which is 8 over 1, which is 8. So my y-intercept is 0 comma 8. And last but not least, we're talking about horizontal and vertical asymptotes. So we always look to factor first. Let's factor a little bit in the numerator. We can factor out a GCF. Doesn't help us a ton. Nothing ends up canceling, but that's still a good process to go through. So in this case, our VA means we set the bottom equal to 0, and so x equals negative 1 is my vertical asymptote. Horizontal asymptote, we are looking at degrees. Degree on the numerator is 1, degree on the denominator is 1. So we look at the ratio of leading coefficients. My leading coefficient in the numerator is 2. My leading coefficient in the denominator is 1, and 2 divided by 1 is 2. So more appropriately, my horizontal asymptote is y equals 2. Okay. So here's just a little word of advice. If we are still struggling with domain, speak up, talk to me, because at this point I'm assuming domain is kind of second nature, and it's going to be a part of our conversation for the rest of the year, so I'd rather get this taken care of now. Same thing with x-intercept and y-intercept. If letter D is still a little bit of a struggle, that's okay. It's a new concept. And hopefully it gets worked out as we start to work through the homework in class. So ask me questions if you have them. As we graph, and this is what we'll talk about first thing, I need you to state and label all asymptotes and then x and y intercepts. So that's why I had you do B and C. And I'm not taking away your calculator for this portion, but I do need to see the work that allows you to come to the conclusion that your graph shows. So, as always, see me for help.